Thank you all for coming. I'm Ian Hickson. I'm one of the co-founders of Flutter, along with Adam and Eric. I designed and implemented a big part of Flutter's framework. Before that, I was the editor of the HTML specification for about 10 years, and I worked on other web specifications for about 7 years before that. And HTML, or rather the web, is arguably the world's biggest platform today, so working on HTML taught me a lot about what approaches work and what approaches don't work when it comes to designing scalable platforms, which we're trying to use now in building Flutter. So what is Flutter? Well, at a high level, Flutter is a high-performance, cross-platform mobile application runtime and its corresponding framework. When I say cross-platform, I mean that it's designed to enable code reuse across platforms like Android and iOS, while also allowing applications to interface directly with native services. So this is distinct from write once, run anywhere, which often leads to a lowest common denominator problem where new features that are only on one platform can't be used until they're implemented everywhere. In this talk, I hope to cover 4 topics. First, I want to give an overview of Flutter's main layers. Then I want to examine a couple of issues specifically in the widgets layer. And finally, I'll quickly cover a few reasons why we believe Flutter is a high-performance platform. So Flutter's layers. We've explicitly designed Flutter to be a very extensible layered system. What I mean by layered is that there are several libraries, and each one in turn depends on the previous one. So our framework does not have a privileged position in this system, and anything the framework does, your code can do too. For example, we've initially targeted material design as our design language, but there's no real reason you couldn't build another widget set on top of Flutter, while still benefiting from much of the work we've done to make the material layer fast. Our lowest layer is DartUI, which is the library exposed by the Flutter engine itself. At this layer, you have a raw canvas, you have our raw text layout API, you have Mojo, an IPC system which we use to talk to the underlying platforms, and you have the Dart core APIs like timers and lists and so forth. The rendering layer, which is built on top of DartUI, is a layout abstraction. With this layer, you can build a tree of boxes and then manipulate them dynamically. And the tree will automatically update the layout to reflect your changes. The widgets layer is a composition abstraction. Each class in the rendering layer has a corresponding class in the widgets layer, but in addition, it allows you to define combinations of classes that you can reuse. Finally, the material layer uses the widgets layer's composition primitives to implement the material design controls. So let's visit each of these layers in turn. Since I'm a big fan of trains, I'm going to use as a demo application a wish list of model trains I want to get. Here's what I want to build. It has material design checkboxes, a material design toolbar. It has an animated material design ink splashes when you tap on the rows. This would be pretty easy to write using the material library. It's a lot more tricky to build from scratch. So to keep things simple, I'm going to set my sights a little lower. It's the same basic layout, but it doesn't have the material widgets. So to do this in raw DartUI, without defining an abstraction layer, we have to manually calculate each coordinate of this table. It's not pretty code. So for example, we have to first calculate how wide the first column should be, and then how wide the second column should be, and then how high each individual row should be, where to put the images, where to lay out the text. This is just a tiny snippet of the code that paints the application. The whole rendering function is about 100 lines of code, and it's all dense math, just like this. Maintaining this code is a nightmare. When I first wrote this application, I didn't have the green dot checkbox control. When I tried to add it, I had to carefully work out exactly which calculations had to be updated and which didn't. If you were to decide that each row should have different padding on the left and right than the top and bottom, you'd have to go in and individually tweak every line of code to make sure you got it right. It would take forever to debug, and it just doesn't scale. Another disadvantage of this approach is that without a layout abstraction, you have to recalculate all these coordinates every frame. This is a lot of calculations that we really should cache, but doing that without an abstraction layer is even more fiddly than the math. The overall architecture of the application of this layer, though, is very simple. There's just one function, render, which gets called by Flutter's engine when you draw the application on the screen. That's what the window.onBeginFrame call does. And whenever something changes, for example, when we get an image back from the network or when the user taps a row, we just tell Flutter that we'd like to redraw it, and it calls the render function again. You wouldn't want to use the DartUI layer directly, but you might build your own abstractions on top of DartUI if your needs were very different from a typical application. For example, if you're writing a game, you might make yourself a game library that targets DartUI directly instead of going through our framework. That's actually all the Flutter framework is. It's a set of abstractions on top of these lower level APIs. The drawing API from this layer is actually exposed at the higher level layers as well. So for example, some of our widgets, like the checkbox, the material checkbox, and the material radio button, they just draw themselves directly to the canvas. They don't have any complicated layout to worry about. They just draw a circle and a dot or a square and dot and so forth. The next level up is the rendering layer. So the rendering layer tries to solve the problem of having to manually compute all the coordinates of the layout. It's a layout abstraction. Rebuilding that demo application using the rendering layer results in very different code. There's no fiddly arithmetic for one. It's all handled by the rendering layer. The application ends up split into two parts if you do it at this layer. You end up first with a description of the application's layout using a giant nested tree of constructor calls, which creates a tree of render object nodes. These are the objects that have a well-defined protocol for layout, painting, hit testing, accessibility, and so forth. And then whenever something changes, for example, when we get an image back from the network, or whenever the user taps a row, we go and mutate the objects that were created in the original setup. So for example, here's a tiny part of the tree construction. The render decorated box you can see here is what sets the background of the screen. I haven't shown how it's actually configured, but you would just have a constructor argument that sets the color. And then deeper in the tree, we would have, say, a render image to draw the little images of the trains. Again, I haven't shown that you would pass it, but it would be an image object that has the pixels. You can see that we keep a reference to the render image object here. We need one for each train. This allows us to update the render image object when we actually get the pixels back from the network. Oops. So this is what the updating code looks like for the image. When we get the image info object back from the network, we just set a property on the render object to update it. This triggers a repaint automatically in the background so that the application gets updated. The properties we use for updating the render objects typically match the arguments that you would pass to the constructor. The advantage of this approach is that you can cache the layout computations. And indeed, we aggressively cache the layout computations in the rendering layer. So in our demo application here, all of the coordinates for each row have been stored so that when we repaint the row, we don't need to recalculate them. Whenever you tap a row in this application, the green dot in the first cell either appears or disappears. The way I implemented this is just to make the dot invisible without removing it from the layout. This means that when it appears or disappears, we do nothing but repaint the application. We don't have to redo any of the calculations. The disadvantage of this approach is, like I mentioned, there are two code paths. So here's the code that changes the opacity that I just mentioned. The top part is the initial build, and the bottom part is when you tap a row. It's really easy for this to get out of sync. Maybe you update the build function to have two different parts for the checkbox. Well, if you forget to add the second part to the updating code as well, then what might look right when you launch the application will look wrong once you interact with it, and so forth. This can be really hard to debug. It can be very subtle to figure out why some things are not working and other things are. It's not as bad as the arithmetic that you have to do when you're laying this out manually at the DartUI layer, but it's still a problem. One reason you might use the rendering object layer directly is if you like this style of programming. It's very familiar to a lot of authors because it's how things have been built for years. The web, for example, has a persistent DOM. Android has a persistent view hierarchy. iOS has a persistent object hierarchy as well. You could also use the rendering layer as a primitive for another layer written on top of it. For example, you could write a templating language that reads a file layout and then builds the render object tree out of it. Moving up one more layer, we get to the widgets layer, which is in fact built using the rendering layer. So the widgets layer solves the problem of having to build the tree and maintain the tree with two different code paths. Instead of explicitly building a tree and then dynamically mutating the tree, you just create a new tree of immutable widgets each time you have an update, and then you hand it to the widget layer's RunApp function. The first time you call RunApp, it takes the tree of widgets and creates a corresponding element object for each one. And those elements then each create a render object instance that corresponds to the widget. When you call RunApp a second time, it reuses the elements whenever possible, and if the elements were reused, then rather than creating new render object objects, we merely update them. Now, that was probably quite confusing, so I'm going to go through this in more slow detail here. So here's an example using some fictional widgets to keep things simple. Suppose we have two widgets. One is a rectangle, which in this case has its color set to green, and one is a circle, which has its color set to blue. The types of the widgets are their shape in this case, and they have properties which give the color. The rectangle widget would have a corresponding render rectangle render object, and the circle widget would have a corresponding render circle render object, the render objects being from the layer below. Now, the difference between the render objects and the widgets is that the widgets are immutable. You can think of them like literals. They describe the configuration of the render object, but they themselves have no associated behavior. Once you create one, it never changes. You could create them with a const constructor in Dart, for example. If you wanted a yellow rectangle, you'd have to create a new rectangle with that configuration. You couldn't change the green rectangle widget into a yellow rectangle widget. This also means that the widgets are relatively cheap memory-wise. They have only their configuration, whereas the render objects are quite heavyweight in comparison. They have all their current size, their current position, and so forth. The render objects, on the other hand, are mutable. So, for example, if you had a render rectangle with a color, you could set its color multiple times and change it each time. You can think, again, of widgets as a description of the configuration that a render object would have. So when you call RunApp with this widget tree, it creates a parallel tree of element objects. Element objects have a reference to their current widget, which we also call their current configuration. But they don't really know much about anything except how to compare widgets. So they also hold a reference to the render object that corresponds to the current widget. To get that object, they call a method on the widget that creates an instance of the appropriate render object class. For example, our hypothetical rectangle widgets would create render rectangle render objects, like this. Notice that when the render object is created, it's created with the settings of the widget, in this case green. As I mentioned earlier, when you use render objects, you have to have two code paths, one to create the tree and one to configure it. Well, in the widgets library, these two code paths do still exist. They're in methods called create render object and update render object. But they're buried deep in the framework, and you'd only see these if you were building a widget for a new render object of your own creation, which you can do. Next, the element looks at its widget to see if it has a child. In this case, it does. It has a blue child, a circle child, rather. And then it creates an element child to handle that child widget. So it creates the element, hands it the widget, the element, the child element now, the second one, in the same way as the first one asks its widget to create its render object. Then the element hooks up the render object to the parent element's render object, and thus we get our three parallel trees: the widget or configuration tree, the element tree, and the render tree. The render tree then gets laid out and painted just like if you weren't using widgets, just using the render layer directly. In practice, when you're dealing with the framework, you don't see the element tree. It's kind of abstracted away. For those of you who have played with Flutter before, the build contexts that you see all the time, those are actually the elements, just under the hood. Now, the interesting part of the widgets framework is what happens when you create a new set of widgets and call RunApp again. So let's move our first tree of widgets up. We create a new tree, a new configuration. So same types of widgets, rectangle and circle, but they have different values, yellow and red. Again, these are new instances. We couldn't have changed the earlier widgets to have these new colors because they're immutable. This is what lets us have just one code path for updating objects rather than two. If we made the widgets mutable, which you might think is a good idea, well, I just want to change the widgets. If you made the widgets mutable, it would be no different than the render object layer. So if you like that strategy, you can just use render objects directly. That's what that is. So let's put this yellow rectangle into RunApp. First, it looks at the yellow rectangle and the green rectangle, and it's like, they're both rectangles. So they're the same type of object. It decides they are compatible. It asks the rectangle widget to update the render object rectangle, and therefore that one is now yellow, and then it drops its connection to the old widget. Now that old widget might now be garbage collected. You could also reuse it. You could call RunApp again with that green widget. It would just mean that the tree should once again be updated to show a green rectangle and a blue circle. Since the widgets are immutable, by the way, the children are part of the description. You couldn't take that green rectangle and give it the red circle as a child because the child is immutable. The child connection is immutable. It is and always will be the blue circle. The parent-child relationship in widgets is one way, so the same blue circle widget could be a child of various different parent widgets. This is not true in the element tree or the render object tree. Okay, so continuing now, we have our yellow rectangle is all updated, but we now need to look at the child. So the root element looks at the child of the widget, sees it's the same type, circle, as it had last time. So it asks the circle to update the render object, and then cuts its ties to the old widgets, and they go away. And then we have our new tree. So let's do one more of these to see what happens when the types don't match, because that's an important case. Suppose you were to create a new widget tree that had a rectangle, which was the same color as the old one, but it had a different child, so a different widget. The fact that it has the same color doesn't matter. It will still update the render object when asked to. I just didn't want to have to change the colors on all my slides. So the first part goes off exactly like before. We connect the new rectangle widget to the element. We can see that the same type. We ask them to update the render object. And that all happens. We lose connection to the initial render object. Next, we look at the child, and we see, aha, we have a new child. It's not the same as the old child. It's not even the same type, in fact. So we cannot use that widget with this element. That also means we can't use that element at all. So we're going to disconnect that element. You have to deactivate it. And then when you deactivate an element, you also detach the render object that it was managing. So all of those bits get torn out of their trees, whoop, and they're no longer referenced, so they go away. And we could actually reuse those. In fact, we have some logic to reuse them in certain cases, but we won't go into that in this talk. So we now create a new child element. We hook it up to the new widget. The new widget creates a new render element, a render triangle in this case, and the render triangle gets hooked up to the render rectangle, and now we have a new tree, a new render object tree. Okay, so this is what it looks like when you invoke RunApp. It's a similar to in the render object level, it's a tree of constructors. These objects are all widgets that configure render objects. So each one takes a child or a list of children, or in some cases it has no children, like raw image is a leaf, so it doesn't have a child. The main difference between this and the render object level is that we just create new widgets each time instead of having to maintain references to the previously created widgets. So you'll notice there's nothing taking a reference to the raw image so we can update it. We just call RunApp again when we have a new image. The problem with this approach is we have to explicitly call this render method to call RunApp whenever our current description of the app changes. So this doesn't scale. Say you have hundreds of these objects. You don't want to update the entire tree every time one image changes. So instead, we have a widget we call Stateful Builder. And a stateful is different from the widgets we've seen so far in two ways. First, it doesn't have a corresponding render object. And second, it doesn't have a child. It has a builder callback. When it comes time to obtain its child, instead of just returning it, the element calls the callback and then uses the return value from the callback as if that was the child. This lets you build your entire app with one call to RunApp and then never have to call RunApp again. And anything that changes will just cause the relevant part of the subtree to rebuild a new set of widgets. To extend our earlier example, this is what the diagram would look like. Notice there's no render object connected to that element in the middle. I've also renamed the elements here to be more close to their real name. So you have render object elements, are the ones that manage render objects, and stateful elements are the ones that manage the stateful builder. The callback, which I've drawn here as an oval with the last return value inside it, is what the stateful builder has. It doesn't actually have a pointer straight to the triangle. Sorry.
So go back.
Yeah, you bet.
To the diagram. What's the relationship between rectangle yellow and stateful builder?
Child relationship. The rectangle yellow has a reference to the stateful builder child. So the interesting part of the builder callback is actually the set state callback, which the builder callback gets given as an argument. When you call this set state callback, it causes the tree to spontaneously rebuild from the stateful builder whose set state you called. So let's do that with this diagram. Say you call set state, and then the next time it calls your builder callback, you return a square instead of a triangle. Well, from that point on, it does exactly the same as it did before. You drop the old widgets because they're not the same type. You create a new element child, and then you create a new render object from that square widget, and then you connect it up to the render object. Notice that the rectangles at the top were not visited in this walk. We just started at the stateful builder and we went down. We didn't do anything with the rectangles at the top. So I've been throwing this word state out a lot, and it's probably a good time to clarify exactly what this means. State is anything that impacts how the application renders. There are lots of things that are state. Some things might not obviously be state. So for example, user data in the application is showing its state. In our little demo app, that'd be the state of the checkboxes. Each row can be checked or unchecked. That is state. That's the most obvious kind of state. There's another kind of state in that application, which I've mentioned before in this talk, which is the images. When you need to fetch an image from the network, you don't have the image immediately when you first draw the app, and then later you get it. The fact that you have the image, the dimensions of the image, the pixels for the image, that is all state as well. So when you get the new image, you then have to update your tree with the new state. In our demo application, though, there's actually one more piece of state that might not be obvious, which is the orientation of the screen. Actually, more precisely, the dimensions of the screen. So when you rotate the phone, now the app has to rebuild. And the reason it rebuilds is some piece of state, namely the orientation, changed. There's lots of other examples. You could have an animation, the current position of the animation is state. You could have something that scrolls, its scroll position is a state. The operating system has tons of state. The file system, in fact, could be in a way state. The other question is, where should you put the state? Where should you hold it? Well, again, there's many different answers to that question. So far in this demo app, I've mostly used the system environment for the screen dimensions and global variables for everything else. I'll get back to that in a second. But just to recap, state, if you want a precise definition, is something that can be synchronously read while the tree is being built, and for which we will be promptly informed whenever it changes so we can schedule an update of the rendering. Once you have that definition, you realize a lot of stuff is state that you might not previously have thought of as state. Okay, so if we look back at Stateful Builder, it solved the problem of how to limit how much of the tree is updated when something changes, but it didn't help us with where to put this state. Like I said, I have it all in global variables in the demo. That doesn't scale. If you have an application with millions of rows of data and it's all state, you can't just have that all in a global space. So instead of a callback, let's make a separate object to maintain the state, and then we can put the state as a property of that object. So this would be an object that would be reused as is when the tree is rebuilt in the same way that a render object is reused. Something like this. Stateful element would have an object, just like it has the render objects in a render object element. A stateful element would have a state object. Now, we could make this even more convenient if instead of a callback on Stateful Builder, we had Stateful Builder just call a method on this state object that we provide. That way we'd only have to provide one object, not an object and a callback. That would be somewhat more convenient. And that's actually exactly what Stateful widget is. It's a widget with an element that holds onto a state object in much the same way that a render object widget has an element that holds onto a render object. A lot of our widgets subclass stateful widget. For example, the network image widget subclasses stateful widget to track the current state of an image download. When the image comes in, it calls setState on itself in the same way that we had a setState callback before in Stateful Builder, and this causes just that little part of the tree to rebuild. In the case of network image, that is literally just the leaf, because network image has no children. So this is the skeleton of a network image. It will be the state object, the network image state, will be kept for as long as the network image is able to be synced with the stateful element. So anytime we can reuse the stateful element, we continue reusing the same network image state. When the element goes away, so does the state, just like before with the render objects. Within the network image state class, you refer to the config property, which is a pointer to the current network image widget. This is how the network image state would find the URL of the image to show, for example. Now, as you might expect, once you have a stateful widget, stateless widget sort of falls out almost by default. So suppose you have some set of widgets which you always kept together. For example, say you have text and you want to always put padding around it. In the demo app, that actually happens a lot. Every time you see a cell with text in it, there's like a 4-pixel padding all the way around. So you might imagine you want to factor that out so that anytime you put text in your app, you can just say, I want text with padding, padded text, say, and then it would automatically put in the padding around you. So you could use a stateful widget to do this, right? You could build a padded text state, which has a build, which returns this padding and this text. And it would get the text from the padded text widget. This is kind of awkward, though, because we have two classes and a bunch of boilerplate to do what really could be done with a single function. So we need the widget class, since that's what we put in the tree. But if we make our state's build method simply defer to another build method on the widget, we'd end up with a state class that looks pretty much the same anytime we do this. We could call it stateless state. And then we could reuse this anytime we make one of these little templates, just like here. And that is, in fact, exactly what stateless widget is doing. It is just a widget that has a build function on it, and then its element knows to just call its build function directly. So once you have stateful widget and stateless widget, you can make lots and lots of reusable components that are composed out of one another. For example, if we can have a container class that uses padding, decorated box, constrained box, and so forth, and then you can get all these effects with a simple call to container. And then we can have an animated container class that combines a timer and calls a setState to continuously rebuild a container class with slightly different values, so that, for example, you can fade a box decoration from one color to another. Now, when you want to fade a box from green to red, you just say animated container, you say what colors you want to fade to and from, and it just does it without having to worry about calling setState yourself. Now, you could use the widgets layer directly, or you could build a set of predefined controls on top of it, and that's actually what the material layer is. It's a set of controls that implements the material design specification built using the widgets layer, which itself is built using the rendering layer, which itself is built on top of the DartUI primitives. For example, in my little demo app, in the material layer version of it, it has an app bar widget, which is called, as you see here, and this is just making the toolbar at the top of the screen. And with just this one call, I'm able to get the right shadow effects and the right fonts and the right alignment and so on. And to do that, the app bar class itself has a 100-line or so build function that uses a lot of other widgets like size box and container and padding and column and so on to obtain the effect of a material design app bar with the right height and the right shadows and the right scrolling behavior and so forth. The reason you use the material layer is obvious. It's a high-performance, high-fidelity implementation of the material design spec, which works on Android and iOS. So if you want to write an application for Android or iOS or both and use material design, then it's the perfect fit. Okay, given everything I've described so far, you might be concerned that Flutter is going to be really slow, especially with big applications. The 3 trees I've talked about are non-trivial. We're talking hundreds and hundreds of nodes. And walking trees isn't especially fast. Creating new objects every frame sounded to me when I first saw this design horrifyingly expensive. So to close out this talk, I'm going to quickly mention some reasons why Flutter is actually fast, despite this. The trick is that we've used a lot of tricks. There's not just one answer. First, we don't actually walk the entire tree except the first time it's built. All the trees are carefully designed so that they can be updated with surgical precision. So for example, when the render object tree needs to be relayed out, we actually only lay out the parts of the tree that changed. So if this was just the render image at the bottom getting a new image, and it didn't change size, we would only relay out that one object. In fact, we wouldn't even need to relay it out, we just repaint it. I haven't talked about painting much in this talk, but we have similar tricks on that side. We only repaint the part that we need to repaint. On the element tree side, when we're walking a tree to do an update, we abort the walk as soon as we see a widget we've seen before. So I mentioned before that the blue circle could have different parents. Well, say you had, say you updated the rectangle and then gave it the same circle, we would update the rectangle, do all our logic for there, look at the circle, see, it's the exact same circle as before, and we would just abort the walk of the tree at that point, since we know nothing below it can change because of the immutability of the trees. We also make good use of our knowledge of the underlying VM. For example, in Dart, allocating many objects in a row is not that expensive. It doesn't involve a malloc, for example. The framework's design is also intended to limit the number of polymorphic call sites to a very few well-understood places that we can micro-optimize. We've worked closely with the Dart VM team and continue to work with them to improve performance and to better understand what we can do to make it even faster. We also regularly measure our performance, and if we find new bottlenecks, we work to get rid of them. We're trying now to make this automated so we can catch regressions as soon as they happen, which will help a lot. And another reason we're fast is that we try to prevent you from doing slow things. There's a number of features in our engine that we simply haven't exposed. For example, we don't have an immediate mode text API. Drawing text is expensive, so we strongly encourage, even at the DartUI layer, using primitives that allow you to cache the text layout computations. And finally, one of the benefits of the design I've described here is that we can split out the functionality into tiny little classes. We don't have one render object that knows about padding and sizing and flex layout and stack positioning and so forth. Instead, we have one tiny class that knows about padding and one class that knows about sizing children and one small class that knows about flex and one small class that knows about stack positioning. This helps make it very obvious when the code is going to be slow because there just isn't that much code in any one place. And the ways the various classes interact is limited to well-defined protocols that we can examine carefully. In the demo app, there was a table. Tables are actually very expensive because you have to remeasure each column and walk all the different cells and figure out how wide each column should be every time. But if you don't use a table, you don't pay that cost. And that is one of the advantages of having this very composable approach. And this brings me to the end of my talk. Thank you very much for coming. I hope it was very useful. If you want more information on Flutter, please do look at these links. In particular, the second link is our Dart docs, and we've been adding a lot of documentation there recently. And I shall now take your questions and maybe answer them, if you like. Also, for people who are remote, I'm going to attempt this slides Q&A feature. Did that work? That did work. I don't know what this does, but maybe your questions will appear on my screen. I don't know. Yes?
So other than having my app slow down, is there some way we can detect tree relayouts that are happening far more than we want? In other words, we unintentionally cause the tree to relay itself out?
So the question is, can we detect when the render tree is being laid out more than it should? That's a good question. It's hard to do that completely automatically because we think it needs to be laid out. That's why we're laying it out. But we can probably dump metrics about who is being laid out, which could be helpful. We haven't done that yet, but we should definitely follow up and we'll look into that. Yes, in the back.
Does animation use the states that you're talking about? And does that require a lot of rebuilding or rematching elements on every single frame, or should it be more optimized than a thread?
So the question is, does animation use this mechanism, the set state mechanism for its animation? Yes, it actually does. But it actually turns out that it's very fast. Because the way that you would, so say you have an animated container or transition or something, you would create it and you would give it the children it should have below it. And then inside the animated container, it would say, okay, call me every time, every tick, say. And then I'm going to call setState. And in its build function, it will do whatever it is it's animating, say changing an opacity or changing a background color. And then it would include as its children the children that you gave it. And so when we update the tree, this ends up being really fast because we just start at the animated container. We look at its the value it returned in its build function, and that's a new opacity, say. And so we update the render opacity. And then we look at its child, and that's the exact same widget you had last time, the one you passed in to the animated container. And so we abort the walk. And so we actually only walked 2 elements. We walked the top element, which is the one that got set state, and we walked the one that it built, and then we aborted the walk. And so this ends up being really fast. Yes, sir?
So when the widget layer mutates these render objects, I assume it would be mutating multiple properties, so the background and foreground and so on. Does the recalculation of the layout and repainting happen as a batch, like after all of these mutations happen? Or is it as one of these properties on render object is being mutated, the whole thing?
So the question is, the render objects layer, when you make a change to one of the render objects, do we batch these changes and recalculate? Yes, very much so. We actually do nothing at all for, say, 16 milliseconds or however long it is until the next frame is due. And then when the engine, if you remember right at the very start of the talk, I showed what it looks like at the lowest layer. You have a on begin frame callback. When the engine says, okay, it's time for our next frame, then we go through a very phased approach. So first we look at the widgets layer and we rebuild everyone that needs to rebuild and update the render objects. But the render objects just store the new data. They don't do anything with it yet. Then we enter layout mode and we walk all the render objects that are dirty and we tell them, okay, figure out your new positions, your new sizes, and so forth. Then once we've done that, we enter paint phase and we tell everyone who needed to repaint. Okay, now you repaint, you repaint, you repaint. And then if you have accessibility turned on, we do the same thing with accessibility. But yes, it is very much one after the other, separate phases.
So does this mean there is no API to really calculate the values? So for example, you would set the width of something to some relative value, and you want to kind of read what that ended up being in terms of pixels. Right. So there is no API to be able to calculate.
So the question is there a synchronous, basically a synchronous way of reading layout? So somewhat similar to, say, inner width in HTML. Yes and no. So no, there is intentionally no API to do this at the render object layer in the tree that is being displayed on the screen. And that's very intentional because doing layout is expensive and you only want to do it once per frame. You also actually in practice end up not needing it very much because it's all little composed bits. You can just build a new bit that does the layout you want. So for example, the material applications have a scaffold which displays the toolbar at the top with all the scrolling crazy stuff that material does. By crazy, I mean awesome. And puts the button, the fab, the floating action button at the bottom right, and puts the drawer there and so forth. We just have a function that knows how to lay that out. And so it measures the children and it figures out how big they are and it just puts them in the right place given their sizes. And so you don't actually need to set something and then read it and then set it again and then read it. However, if you did want to do that, you actually could do that. As of relatively recently, I don't see Chris here, but Chris just changed our system to support off-screen, essentially, render object trees that have their own pipelines. And so you could build a separate tree, force it to layout, and then measure it, and then use that to work out what's going on if you wanted to. We have a question from the audience here. Let me see how this works. Hi. Awesome. It's Seth right here, apparently. Do you have advice for when to use stateful versus stateless widget? Yes, use a stateful widget when you have state, and a stateless widget when you don't. I don't know that I can put it any simpler than that. I mean, under the hood, they're basically the same thing. They're actually not. In the presentation, I explained that you can build a stateless widget out of a stateful widget. In practice, we have a slight optimization so that we don't actually ever even have the state for a stateless widget. But, I mean, that optimization really is neither here nor there, really. Yes?
Not to confuse the question, but the place I see the real trick is where should the state be kept? I mean, quite often you can keep it in the parent as a stateful widget, which ripples it down to the state list and just. So that's the place I see the question coming up.
Right. Yeah, the question of where to put the state, I kind of touched on that briefly in the presentation, it's a question that I don't yet have a fully good answer for. I have an answer for any specific case, but I haven't quite worked out the way to phrase a general answer. Adam, have you thought about that? I know this is something you've looked at as well.
I mean, this is the primary design question.
Yeah, I'm just basically said for the people out of the room that it's just a question of how you design your app. This actually is a similar question you have to answer when you're doing more traditional, if you were targeting the render object layer directly, you still have this question, like where do you put your state? You could put it in a render object, you could put it in a global, you could put it in your own model of the app and then keep passing it around. Like there are various options. Yes?
Yeah, I was going to say, if you have MVC, it's kind of just asking, which ones you didn't have.
Right.
So I think if you have state the widget, that would be a view layer. But I have another question. So if you have, like, I don't know, let's assume you have one object animating, just like a bouncing ball bouncing up and down, and then mid-animation, you sometimes have something else in the UI, like a really expensive text layout or like a really expensive table layout. Would that cause visible stutter in the animation, and is there ways to in the bouncing ball?
Right. So the question is, if in one of your frames you have some much more expensive work to do at the same time as you have a running animation, will you be able to notice in the running animation? Yes, you will be able to notice in the running animation.
How can you avoid that?
We haven't actually, so there's several ways you can avoid that. One of them is to not do anything expensive, which sounds flippant, but actually is basically what we've done so far. We often find that you don't have to build the app with something expensive. So in the example, the demo app, I could have put in the green ball and then entirely removed it and relay out the entire table as if the ball wasn't there and then put it back in when you tap the row to put it back in. And that would be very expensive because you'd have to remeasure every cell to work out the new table dimensions. But in practice, you don't do that. You just always have the ball there and just switch its opacity from 1.0 to 0.0, which is a really efficient change. So yeah, like I said, flippant answer, but that in practice is actually much more effective than you might imagine. The other answer is, so again, we can use the fact that you can build a second tree separate from the main one that's being rendered. This is completely hypothetical at this point because this code literally only landed like less than a week ago and hasn't been used by anyone yet. But in theory, yeah, you could imagine putting the new tree in a separate isolate and then somehow transferring that information over. We haven't built that yet, but that is something we looked at very, very early on in the project, back when we were still using JavaScript as the language, is how can we make layout, at the time we looked at, we make layout entirely asynchronous. So that it's interruptible. So you're halfway through a layout, you're like, it's time to draw the frame. Okay, well, we haven't laid out this part of the table yet, but whatever, we'll just paint what we have. The design we had at the time doesn't work in practice because the overhead of having everything be asynchronous is so high that you end up missing every frame. But in principle, you could do something more coarse-grained than that. It's something we need to explore. Yes?
Was the repaint boundary and the repaint rainbow? I don't know if you want to talk about that.
Yeah, you asked about repaint boundary and repaint rainbow. So we haven't. I didn't talk about painting much in this talk, but yes. So repaint. I described the three trees: the render object tree, the element tree, and the widget tree. We actually have even more trees than that. on the right, I guess, of the render object tree, you have a paint tree. And on the right of that, you have a layer tree. I guess you already have a paint tree. You have the render object tree, you can generate a layer tree. The repaint boundaries are a way of saying, okay, I want this subtree of render object nodes to get painted to one canvas and make that canvas separate from the canvas used for the parent. I guess I should say picture, not canvas. And so if you have something that is animating very fast, then you could, like say you have a scroll list. You have a complicated application, and then in the middle of the application you have a list that scrolls. When you repaint your scroll list, you really don't want to have to repaint the application on the outside. So you can put a repaint boundary around the list, and now when the list says I'm dirty and need to repaint, we only repaint the list, and then we reconstruct the scene using the previously painted picture for the outside, and that's much more efficient. And in fact, that is what our list widgets do. They have a repaint boundary around their outside, and they have a repaint boundary around their insides. And so when you move the list up and down, we actually don't repaint anything. All we do is shift the picture of the inside a little, and maybe repaint a new row at the bottom if a new one's available. Does that answer your question? I'm not sure if I don't know how much detail to go into.
Yeah, I just thought it would be useful to mention because for me that was a gold mine, and the repaint info for debugging helped me understand.
Oh, right. Yeah, so we have a bunch of debugging tools. If you go to Flutter.io, there's a link to a debugging page which talks about a lot of them, although we've added even more since then that haven't been documented yet. And one of them is this repaint rainbow. And the repaint rainbow will draw a color mask, essentially, over every layer that is painted. And anytime it is painted, it changes the color slightly. And so if something gets repainted a lot, you'll see that color cycle through really quickly. And so if you have a part of the application you know should never change, like say the toolbar, and you load your app and you see it's color cycling a lot, you're like, aha, I know I should put a repaint boundary around this. We also have, I don't think anyone's ever used this to figure out anything useful out of it, but I would love you to look at it. We have metrics now that get dumped in the render tree dump. There's a function called dump render tree, debug dump render tree, which dumps the entire description of the tree, the render object tree. And included in that for every render repaint boundary is metrics regarding how often the boundary was useful. So how often its parent was painted and it wasn't, or its child was painted and its parent wasn't, versus how many times both the parent and the child painted at the same time. And so in theory, that can help you determine, like, is this repaint boundary useful or is it just wasting memory? I'm just going to do some of these online questions since we have more here. Are there any language features that Dart could add to make our rendering layout animation code faster? Probably. That's probably a question we should take offline. I don't know if any, I wouldn't be able to say offhand. Yeah, or Adam. Adam's been working on this in particular.
I have a related question.
Yeah?
How have you found garbage collection calls interacting with Flutter?
So the question is, what has our experience been with garbage collection? This is something of a moving target. Is my understanding the Dart team is moving to a concurrent garbage collection model? Is that right? Yeah. Adam's nodding, so I'll take that as a yes. Right now, garbage collection can sometimes be a problem. If you have a long-running animation, you'll sometimes see it stutter as big garbage collections happen. But we're looking at various changes. So we're looking at, like I said, concurrent garbage collection. We're also looking at making smaller garbage collection sweeps more often. Right now, the VM apparently is being more optimized towards server-type applications where it doesn't matter as much.
That's definitely a problem. I mean, it came to my head with garbage collection was one of the parts of Jank that you couldn't really control.
Yeah, so we're very much we're very aware of that problem, and we have plans to deal with it. We haven't finished dealing with it yet. One more question here is, in Flutter animation and gesture detection are both treated as widgets the same way as concepts like layout and rendered views. Why are all these different concepts grouped together in the same category? Why not, I guess, is the answer. Once you build once you have this stateless widget and stateful widget concept, it ends up being very easy to describe anything that affects the tree geometrically in the same way. So accessibility, so gestures, and so forth, animation, they all affect the tree in the same way. So this is it's more a matter of convenience, I think, is a way to describe it. Yes?
There is a non-widget animation library.
Yeah, so right, I didn't talk about all the layers in the layer diagram. We actually have more layers than I showed. Between the DartUI layer and the rendering layer, we have an animation layer and a painting layer. The animation layer is just about how to manage your timers, essentially, and how to convert a ticking clock into a varying value of any type, like a varying color or variable double. And then the painting layer on top of that, actually it might not be on top anymore, it might be next to it now, is about convenient primitives for painting boxes and pictures and so forth. And then the rendering layer is built on top of those, and the widget layer also reuses both of those. So the widgets layer really, the way to think about it is a way of combining features that are below it. So it combines the animation logic and the render object logic and the painting logic into reusable components. That's really the way to think about that layer.
So if you were going to switch to, say, a physics 2D layer instead of, padding and that kind of stuff, you could actually just not include that in the tree and then have that off for secondary non-visible widget.
Right, so the question is how would you approach integrating 2D physics, say, into the layout based on 2D physics into this? So there's actually several ways to do this. We have a library called Flutter Sprites that actually integrates with Box2D. And the way it does it is it basically has an adapter from the render object layer to its own its own world, if you like. And then within its own world, it can do whatever it likes. You could also approach this by the render object layer is very flexible in terms of how it configures things. For example, it doesn't actually have intrinsically an opinion about what coordinate system you use. So all of our render boxes are render boxes, and they have an opinion that you're using Cartesian coordinates. But render box is actually just a subclass of render object, and render object could do other things. And so you could subclass render object to have render physics, and then do things based on physics in that way. I wouldn't want to pontificate on exactly what approach is the best from a podium, but I mean you'd have to look at the various options. One last question from the back here.
One of the other things that Android often tries to optimize is overdraw. It sounded like from what you're talking before that we might built-in support for void overdraw.
So the question is, do we, in contrast to Android, do we have built-in support to avoid overdraw? It's built in to some level. You have to opt into it. You have to explicitly say, this is the part of the tree I want to avoid repainting separately from this other part of the tree or together with the other part of the tree. Some of our built-in widgets like scrollables take care of that for you for the obvious cases. But if you create your own new widgets, then you have to worry about that yourself. But hopefully we have tools that let you detect when that happens, like the repaint rainbow that we mentioned earlier and the metrics that are now in the render tree. Okay, one last question.
If you have a widget that has a very large number of trial widgets, and let's say the list of those is 2. So if we move items around, how do that? Does the tree walk diff and keep things alive, or does it?
You've noticed the gap in my talk. So the question is, how do we handle child lists essentially at the widget layer? You'll notice all of my examples carefully only had one child. We have, yes, essentially we try and do something slightly clever there. We only do it at one, well, we have two separate answers for this. The first answer, we only do at one level at a time. So we look at a single child list and we compare it to the old child list. And within those child lists, we try reasonably hard to keep things, to find matching widgets and reuse them where possible. Because, yeah, there's a huge gain to be had from if you remove one thing from the list, everything else is the same. You don't want to have to pay the cost of relaying out everything in the list. You just want to remove the one thing. And so what we do is we walk the list from the start, then we walk the list from the end, and then we eventually find, okay, all the leading ones are the same, all the trailing ones are the same, and then we have the middle ones, and then we like walk down the list and work out, okay, so can we skip this one? Okay, you can help the system a lot by giving each widget a key, which I didn't talk about at all in the talk, but every widget takes a key. You can give a key, which is basically just an arbitrary object. We just compare identity. You can give each widget a key, and that will help us a lot in figuring out, okay, these people are all the same, these widgets are all the same, we can keep them in sync. The other answer we have is, so we have this concept of a key, we also have this concept of a global key. The global key is a much more heavyweight key. You can only have one widget in your entire system at a time that has a particular global key. We track where that widget exists at any one time. And if you reuse the global key, like if you build your tree, take out an object from this place that has a global key, and in the same frame put it in here with the same global key, we will notice this, and we will try and reuse as much as possible of stuff we've calculated before in the new place. I haven't looked at how much that gains you from a render object perspective, but I imagine you could probably skip a lot of layout. I don't know if we've tested if that actually works or not. We have tested it? Okay, good. So yeah, that answers that. Hopefully, we don't do tree diffing. We haven't actually found we need to. We don't look multiple levels down. We did look briefly at doing that, and that gets really complicated really fast. So if you're going to be changing, if you're going to be removing nodes and then rebuilding everything below it, we just put a global key at the top of the subtree that gets reused, and then you're fine.
Yvonne just wanted to add 15 seconds here to answer the question about GC. The eventual plan is a fully concurrent GC. Currently, we have a partially concurrent with a stop the world parallelized mode. If you're interested, definitely go talk to that DartUI. Okay.
All right. Thank you very much.